Hello, everybody. My name is Srijani Chatterjee, and in this paper, we present a novel strategy to create training dataset for keypoint detection algorithm for robotic manipulators using Inpainting method. In existing literature, image-based visual servoing in an eye-to-hand setup control the end effector on the image space using specialized markers like Aruko. In contrast, in this paper, our goal was to develop a method that can robustly detect and track natural features on robotic manipulators. Such features can be used for vision-based control when placing artificial markers like Arukos on the robot's body is not possible or practical in runtime. In our prior method, we identified key points on the robotic arm by combining camera parameters and the individual joint position on the arm in the wall coordinate system to project the 3D joint location on the image space, which is the key point annotation for our dataset. The process is depicted in the left image. We repeat this for several configurations on the arm to create a data collection pipeline. The right image is a sample from the dataset where the 10 identified key points and bounding boxes are labeled. This method requires accurate robot and camera model, and the absence of either of these will render the key point identification inaccurate. To avoid these dependencies on the robot or camera models during data collection, we utilize the concept of inpainting to create our key point dataset. Inpainting, in the context of computer vision and image processing, refers to the process of reconstructing lost, corrupted, or occluded parts of an image. In this slide on the left, we can see the bedside table in the first scene and the bench with the people on it in the second scene are removed while keeping the rest of the images intact. On the right, we can see inpainting applied on a panda robot in our experimental setup, where we are removing Aruko markers from the robot's body. In this method, we train the state-of-the-art Inpainting framework, Llama, with raw images of the robotic arm. We also collect a set of images of the arm in different configurations with Aruko markers on it. We create a binary mask around the markers for all the images. We then pass the original images of the arm with markers and the corresponding binary masks to the newly trained Llama model. This process reconstructs the part of the robotic arm in the image occluded by markers as shown in the third image. We annotate the marker centers as our ground truth key points. We combine the reconstructed images and the annotated key points to create a training dataset for a key point detection algorithm. The above image shows 4 key points identified for the dataset creation process. User has the flexibility to identify key points by placing markers on any part of the robot depending on the individual use cases. We train PyTorch Vision's Keypoint RCNN network with the collected data. In this slide, we have images for same configurations of the panda manipulator with and without Aruko markers. The red dot on the image without Aruko markers are the predicted key points using the trained Keypoint RCNN network. As visible, the predicted key points are quite close to the ground truth. We have achieved a 100% detection rate within a 10 pixel margin of error and a 98.75% detection rate with a 5 pixel margin of error. On an average, our method detects key points with accuracy of 2.19 pixels. For our experimental setup, we used a Franca Amica Panda arm and an Intel RealSense D435i camera in an eye-to-hand setup. We used this 3 detected natural features or key points generated by our present and prior method as control features to conduct 20 adaptive visual servoing experiments for each method. The key points generated by our present method are equally robust with minimal noise. The transient response is also similar for both the approaches. We measured rise time, settling time, and overshoot as our performance metrics for both proposed and existing methods and observed that there is a minimum 5% improvement in system rise time, settling time, and end effector settling time. However, there are a deterioration of 1% and 15% in end effector rise time and overshoot respectively. The overshoot being within the range of 5%, the difference is negligible. To assess the repeatability of our proposed method, we repeated 5 experiments for the same initial and reference configuration. The measured variance is negligible. We are able to control the arm in different configurations, including extreme ones, using our approach with smooth trajectories and minimal noise. To summarize, our proposed method used natural visual features without any markers to control the robot configuration. It does not require robot model and camera parameters during data collection or during control. They are flexible and gives user freedom to identify key points at any part of the robot's body at their will. The key points are robust and produce noiseless trajectories. Our model, however, was not tested in variable lighting condition, so far control convergence is only possible in planar motion. As a future direction, we are working on collecting data for configurations with out-of-plane motion and in turn achieve control convergence. We are also working on extending this pipeline to be used with soft or continuum robots. The QR code has the link to our open source data collection pipeline. Thank you.